Okay, so we're going to continue on with what we've been doing with these applications of integration. So, we did all this stuff with like work and force and pressure. Okay, so now we're going to move on to a new subject, which is moments and centers of mass, which is pretty cool. Okay, so let's do it. Sorry, I moved my stuff around and I can't find my pen. Oh, there it is. I was like, where did it go? I was like looking at one to the right, and I'm just like looking at my desk. And I'm like, where is my pen? Okay, so obviously I think you guys know what centers of mass are. So let's draw a little thing here. So you can imagine that you have a really long thin rod, so that its mass is basically negligible. And then you can imagine that you have a weight over here of mass m1, and then you've also got a weight over here of mass m2. So when we talk about a center of mass, what we're basically interested in, what we're basically, okay, wait. Sorry, I was clicking around trying to change something, and today is just not my day, apparently. So you've got these two masses. You can tell that mass 1 is bigger than mass 2, right? So let's just write that down. Let's just say we know that mass 1 is bigger than mass 2. Okay, so the question, when we talk about the center of mass of this system, we're basically wondering where should you put the fulcrum so it's balanced. So we call this a system. So this is a system of two masses. The center of mass is the location where a fulcrum would balance the system. Okay, so we're interested in figuring that sort of stuff out. Now you can tell because the M1 is bigger, you know that M2 has to be further out to do the balancing, right? Okay, so this point right here where the fulcrum will be, we're going to have our symbol is going to be X bar is going to be our center of mass. So X bar is the center of mass. Obviously, it's not literally the center unless the masses are equal to each other, right? If the weights are imbalanced, then you have to sort of move where your center of mass is. It won't just be in the literal center. Okay, so looking at this example is going to help us figure out more complex examples, because really what you're dealing with here is a linear setup. You really could just sort of express this as a line with point masses. I'll explain what I mean by that. So what do I mean by you can just talk about a line with point masses? Well, you can just draw your little line like this. Okay, and then you can say here at the value at x1 on the number line, we have the mass m1. And then we can just say over here at the x value x2, we have the mass m2. Okay, so the x value is the distance from the origin, right? So x1 and x2 are some distances from the origin. Okay. And what we're looking for is this point right here, x bar, which we're calling the center of mass. Okay. And we don't actually really care about x1 and x2. so much as what we really want to know is how far the mass is from the center of mass. So we'll call that D1. And then over here, the distance to the center of mass will be called D2. Okay, so x1 and x2 is where you are on the number line, but D1 and D2 is distance from the point where it would be balanced, right? Because that might not be the same as like the origin. Does that make sense? Like you have to keep that in mind when you're doing all this. And actually, you can like set all this up and solve it. So, does anyone know what the formula for torque is? Or actually, no, let's not talk about that. So I guess what I want to talk about is like let's talk about the force. So if you have your little fulcrum, oh god, burrito, and you have your mass 1, and you have your mass 2. And then this is some distance D1, and this is some distance D2. How much force is that mass exerting? Well, we know that the force is going to be equal to the mass times the distance from the fulcrum. So you get the force of object 1 is m1 times d1, and you get that the force of object 2 is m2 d2. Okay, and then so how do you make it so like when everything is balanced, there's no acceleration, right? So those forces would be balanced with each other. Okay, so we know that the forces would be equal to each other. F1 would have to be equal to F2 if it's balanced. Right, because there would be zero acceleration when it's balanced. In other words, when the fulcrum is placed at the center of mass. And then you can start making replacements. Well, you know that force 1 is mass 1 times d1, and you know that force 2 is mass 2 times d2. And there's actually a nice way to express what d1 and d2 are equal to. So d1 is the distance of our point, our mass 1, to the center of gravity or center of mass. So in other words, that will be equal to the difference or the absolute value of x1 minus x bar. And then what will d2 be equal to? x2 minus x bar absolute value. Because depending upon the order of how you subtract them, it might be negative or positive. But either way, if you take the absolute value, that will give you the distance. Okay, so what do you get? You get m1 times the absolute value of like x1 minus x bar. You get m2 times the absolute value of x2 minus x bar. Okay, and then what you can do is you can actually solve this for x bar. Okay, so looking at this, the way we've set it up, x1 minus x bar, is that going to be positive or negative? Like, looking at the diagram. Yeah, that one's going to be negative. Right, because x1 is still left, so this is going to be negative, and then this one over here is going to be positive. Okay, which means that when we multiply this out, we're going to have m1. Now, because this one is negative, you have to put a minus. So you get minus x1 minus x bar equals m2. This one is positive, so you just get x2 minus x bar. Okay, now you can go to town just like multiplying everything out. You get minus m1 x1 plus m1 x bar equals m2 x2 minus m2 x bar. You can gather all the x bar terms on the left and everything else on the right. So you get m1 x bar, this is negative, so you get plus m2 x bar equals, that's negative, so you'll add it over, m2 x1 plus m1 x1. Plus m2 x2. Okay, then you can factor out your x bar. and divide by the m1 plus m2. So you get m1 x1 plus m2 x2 all over m1 plus m2. So wow, if you know the weights of your objects, m1 and m2, and you know where you place them on your number line, you can solve for where you would put the fulcrum so everything would be balanced. So I'm going to pause for a moment because this is going to be useful to us in a moment. Mm-hmm. You're talking about right here? Where did I get the... Okay, over here, yeah. Oh, okay. So if you look at the one right above it. So this one has an X bar and this one has an X bar, right? So this one stayed on this side and then this one got moved to the other side. So because that was minus, it ended up as a plus over here, and then I needed this one to move to the other side. Right, so it ended up like right there. Okay, so I erase all those little markings. This is M1, X1. Okay, so there's actually some formulas for this. So, okay, this is the formula, sorry. This is the formula for the center of mass for a system of two objects. Okay, very often you have more objects. So let's suppose you have a system of n objects. What then? Okay, and let's suppose that these n objects are point masses. So you have like their pairs. You have an object of mass mi, and it is some distance xi from the origin. All right, so the mi is going to be the mass of the object I. Or the ith object. And then xi is the position of that object on the number line. So you can actually come up with, well, what's the center of mass for this thing of n objects? And we're going to get our inspiration from the formula we just figured out for two objects. If you look at the bottom of the fraction for two objects, what is that? Like, how would you describe that in words? Like the x bar equals the denominator of the fraction is, yeah, total mass. So in other words, what you're going to do is if you have n objects, you're going to sum from I equals 1 to n of your masses mi. Right? So if you have a system of n objects, you're going to divide by the total mass. Now, if you look at the top of that fraction, you have, what are those terms that you're adding together? They look sort of similar to something you might have seen in physics. So do you see how it's a bunch of masses times distances? You heard of momentum, right? mv equals momentum, the mass times the velocity. If you have mass times the position, we call that the moment of the object. So in other words, on the top, you have the sum of all of the moments. In other words, the masses times the positions. And then what do you divide that by? The sum of the masses. So the formula for your center of mass is the total moments divided by the total mass. So this is actually pretty useful because like you can like use it to compute like where you would need to put your fulcrum if you were like going to balance a bunch of stuff. So let's do an example. So example, suppose that you have mass 1 equal to 30 kilos and, or let's say you have, okay, let's make a list. So mass 1, okay, whatever, it will capitalize it. Mass 1 is 30 kilos. And position 1 is it's placed at -2 meters. Say mass 2 is equal to 5 kilos. And it's positioned 3 meters from the origin. Say that mass 3 is 10 kilos. And it's placed at 6 meters from the origin. And mass 4 is 15 kilos. And it's placed at a distance of -3 meters from the origin. So the question is like, where would you balance this? So you just sort of like imagine you've got this plank. And right here is the 0, the origin of the plank. So what do we have? We've got mass 1, which is 30 kilos right here. We've got mass 2. See the little tick marks are 1 meter at a time. Right here is 5 kilos. So like you'd have like some big huge thing. We'll make it look like a coffee pot. And then you've got like a smaller little coffee pot right there. And then over at 6 meters, 1, 2, 3, 4, 5, 6, you have 10 kilos. That's like a little bigger. Let's extend out our little, extend out our thing. And then at -3 meters, over here, you've got, oops, I forgot to put that this was 10 kilos. 10 kilograms, 5 kilograms, 30 kilograms. And then what, you've got 15 kilos, big but not too big, right here. So I don't know, like, here's like Dr. Evil. And he's like, Mr. Bond, I have a proposition for you. You can place the fulcrum and you will live. Misplace it and you die. And you're like, I'm so happy I paid attention in physics / calculus. Because you're like, oh, this is actually not that bad. You can calculate where the hell your center of mass is going to be by just summing your 4 moments, and then dividing by the total mass. Oh, thank you. I like how you already have the number. So like, what do we get on the bottom really quickly? You get 30 plus 5 plus... So let's just like quickly write it out. You get 30 plus 5 plus 10 plus 15. Which is going to be 20, 30, 60. Okay, on the top you get 30 times -2 plus 5 times 3 plus 10 times 6 plus 15 times -3, which ends up being -60, positive 15, positive 60, minus 45. Now what's cool about these moments is they actually sort of tell you the contribution that each of the objects gives to where your fulcrum is going to be. So bigger objects contribute more, right? And it just so happens that these two objects, the -60 and the positive 60, their influences cancel, right? Because does it make sense that perfectly balanced objects... So there's 2 ways you can perfectly balance objects. One is they weigh the same, and then what do you have to do? They have to be the same distance. Now, if they don't weigh the same, the moment tells you how to get them to balance out, right? So even though one of them is 30 kilos and 2 meters away, that balances out with one that's 10 kilos and 6 meters away, right? Because their moments are the same. They provide equal forces. Okay, so what do you get? The negative 45 plus 15 is going to be negative 30. Oh, just guessing. I was going to say, like, this looks like it's actually negative 0.5. I was going to say, like, negative 1.6 does not seem to be correct. But that was good. It was a guess. Yeah, that would have been really hilarious if it had worked. So what do? You place your fulcrum right here at negative 0.5. Boom, and everything balances. Yeah, surprisingly close to the center, I would say, as well. Yeah, it's like pretty freaking close. So what would you actually need to do if you wanted to... what would you need to do if you wanted the fulcrum to be at the center? You have two options. What could you do? If you wanted to do something to make the fulcrum at the center. Yeah, so let's say you can't remove or add weight. Then what would you have to do? So let's throw out that case. Yeah, let's say that the weights are fixed. So then what are your options? Yeah, so we notice that really there's two things that need to balance out. Oh my god, burrito. The positive 15 and the negative 45, if it was at the center, these would cancel, right? So this negative 45 comes from the thing that weighs 15 kilos at negative 3, that's right here. And then the 15 is the one that weighs 5 kilos right here. So what you could do is you could make that 15 bigger, you can move it out, right? So that the 15 becomes like negative 45. Or what could you do? You could take this one right here and you can move it in, thereby making the total force that it provides less. Or you can make the total force that the other one on the other side provide more. But either way, do you see how they both would need to move right by some amount? Because you would need to move the fulcrum right to some amount. So like, do you see how like it's the same basically? Like if you want to move the fulcrum right, you're going to have to move one of your masses right on either of the sides. Does anyone know what this formula is called in statistics? Imagine if your mass was equal to 1 for all of your objects. Then what would this formula become? If your mass was 1, what would you have on the bottom? If each mass was 1. Not standard deviation. Close. Not standard error. So if your mass was 1, what would you get on the bottom? If each of the masses was 1, what would the bottom be equal to in this case? It would be 4, which would be the amount of masses. And what's a formula you know that you divide by the number of objects? The mean, yeah. So this, the center of mass formula is nothing more than a weighted mean. Instead of each mass being 1 and the same amount, the masses are possibly different. So you weigh them, right? Those xi's are like your numbers. Normally for the mean, you would add up all the numbers and divide by the number of numbers. For a weighted mean formula, you don't just take the numbers, you multiply each of those numbers by how big they are. In other words, it weights them, right? Like the heavier something is, the larger an effect it has. Okay, so this is the weighted mean formula. Okay, so now what we're going to move on to is, well, what about in 2 dimensions? Because that was just one dimension. What about if you are operating in 2 dimensions? Oh yeah, sure, I could just go back up. Cool. You got it? Cool. So what if you're operating in 2 dimensions? Does it make sense with the plank, the seesaw, it's 1 dimension because you're thinking of it as a line? So if you're operating in 2 dimensions, what is the balance thing that you're dealing with, basically? Now you have a plane. Has anyone ever used one of those balance boards that you stand on at your desk? Like, you can imagine, like, if you have this, like, piece of wood, and, like, you put, like, different objects on it, like, you put, like, a can right here, and you put, like, another can over here, and, like, another can over here. Does it make sense that, like, somewhere you're going to need to put, like, a little balance point underneath it? So, notice that this balance point now is going to have some X value and some Y value, right? So, like, what's going to happen if I add, like, a huge can on the edge over here? Where is my new equilibrium going to have to be? Like, where would I have to move that, my little balance point to? Like, generally. Like, we don't know exactly, but generally, what am I going to have to do? Yeah, you have to move it closer to the can, the big can. So, like, you're going to move it to some new X value. You're going to move it to some new Y value. And then now you have your balance point, like, right under there or something like that. So, the question is, like, if you need to balance 2-dimensional objects, how do you do this? Guess what this, like, ends up, like, being very important for? Like, that, like, you might be like, yeah, what are objects that need to be balanced that cost lots of money and explode if you fuck up? Oh, what? Bombs, but usually the method of taking the bomb somewhere. Rockets, yes. So does it make sense, like, your rocket, it needs to be balanced. So, like, when you design your rocket, if you, like, put reinforcing stuff over here, you also need some reinforcing stuff over here to balance it. Otherwise, like, when the rocket takes off, if, like, you don't if you don't have these things over here and you have, like, a bunch of extra weight strapped on the side right here, and you start, like, going like this, it's gonna lead that way, right? And then, like, have you ever seen those rocket fail videos? They go up, and then you just see them go like, ah! Like, that's some engineer who fucked up on their job, basically. It's like, this is, like, a big deal. I sort of want to watch, like, rocket videos on YouTube. Like, part of me is, like, really just wants to open up a video and watch them. But I highly recommend you go and watch some. There's some really amazing Russian fail videos from, like, the 1960s. When they were first starting the Soyuz project. They, like, blow up. Oh, the SpaceX one landed the other day? Yeah, think about how hard that is. Like, think about it, you know, because they come back down. Like, it's the reverse of a takeoff, right? So they have to be really well balanced. They can't just perfectly balance it, so actually what they do is they put the rockets on gyroscopes to make it balance. It's pretty crazy. So, like, you have it on this little thing that, like, rotates. So that, like, you can, like, angle the rocket different directions. Yeah! 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 Right. It's pretty crazy because they literally had to, like, place, like, the thing where they watch the rockets from, like, 50 miles away. Because, like, they knew it could go up, and then they didn't want it to, like, you know, come back and fall on them, right? So they're, like, cleared out everything for, like, hundreds of miles, and they're like, okay, let's try this. But I highly recommend you go and watch the old Russian rocket fails. So anyways, so how do you do this in 2 dimensions? Interestingly enough, It's basically the one-dimensional case twice. So what you're going to do is your x coordinate for your moment is just going to be equal to... Oh, wait. Oh, my bad. I wrote that wrong. The x coordinate for your moment is going to be equal to the sum of all the x moments. In other words, the masses times their x values divided by the total mass. And then what is the y coordinate for your moment going to be? Well, it's all of your y moments. You take your masses and times by the y values. And then what are you going to divide that by? The total mass. So it's the same formula, but now you have to do it with x values and for y values. This article called The Rocket Exploding Rapid Unscheduled Disassembly. That is such an engineering book, a joke. I love it. Rapid unscheduled disassembly. I guess you would call like demolitions like rapid scheduled disassemblies. I guess that's also what bombing is. Such euphemisms. Okay, so, I'm not gonna... Oh yeah, the methane leak. Yeah, it's sort of crazy how that happens. I'm not gonna do an example for this because it works exactly like the other one. Well, I'll just sort of tell you like how it would work. So like, they would give you a list like this. So they would say like, well, what's the mass of 1, 2 kilos? And then they have to give you a coordinate, like -1, 3. So does that make sense? This would be an x value, that would be a y value. And then they would give you mass 2, I don't know, 6 kilos. And then they tell you where it's placed at 1, 1. And then they would give you mass 3, I don't know. They'd give you some number of masses, 4 kilos placed at 2, -2. So to sort of imagine what this looks like is you have your plane on which it's placed. You have this one thing placed at -1, 3. So you have this smallish mass at 1, 3. You have a largish mass at 1, 1. And you have a medium mass at 2, 2. Okay, now what you can imagine is that these are basically placed on a wooden board. Assume that the wooden board has no mass, or at least has a uniform mass, or uniform density. Because if it has uniform density, it's not really going to matter. So anyway, so what would you do? You would just take all of the x values and the masses, and you would find your x coordinate, and then you would take your y values, use them to calculate your moments, and find the y coordinate. So right, you'd have like 2 times -1 plus 6 times 1 plus 4 times 2. Right, and then what's the total mass? 12. And then you would do the same thing for the other one. You'd have 2 times 3 plus 6 times 1 plus 4 times -2, and then you would divide all that by 12. So if you go and you calculate it, you're going to get -2 plus 6 plus 8. 14 minus 2 is 12. 12 over 12, you get an x coordinate of 1. Then you get 6 plus 6 minus 8. That's 12 minus 8, which would be 4. So you get 4 over 12. That's 1/3. So apparently, where are you supposed to place your little thing? At 1, 1/3, like right there. And that makes sense. You can see that it's super close to the heavy mass, right? So that heavy mass ends up being very close to the fulcrum, and then your other 2 masses balance each other out. Boom. Okay, so obviously all of this hasn't required any calculus yet, right? So now we're going to take what we've learned and apply it to like a calculus example. And what we're going to be interested in... Oh, did I add wrong? No, 6 plus 4 is 10, and 10 plus 2 is 12. Okay, I was going to be like, wait, did I screw that up? So I like took it really seriously for a second. I was like... Yeah. No, I was like, wait, oh man, that was an epic fail on my part. And then I was actually sort of surprised because I was expecting to be completely wrong. And I was like, no, that's actually 12, oddly enough. I did do that right. No, burrito. Oh, yeah, so you looked at it and you're like, wait, 13. But yeah, that was what I had. Okay, so now what we're going to do... Oh, yeah, everyone's dogs hear burrito. Is what if the density of your thing that you're balancing on isn't constant? What if your density isn't constant? Or what if you have a weird shape? So like, imagine that you have like some thin disc. And I don't know, it looks something like this. So this is actually flat. So does it make sense, that disc, that's like you have a little plate that's like shaped like this? Okay, so does that make sense? Like you have this thing and you're wondering like, where where would I place my little fulcrum underneath it? Okay, that's like drawn really horribly. Where would I place my little fulcrum on the plate so that it would balance? Because you can see like if it was a circle, where would you place the fulcrum to balance it if you had like a circular disc? So if you had this like disc, yeah, right in the center. And that makes sense because what happens is if you like draw any single line that goes through the center, does it make sense like this point over here and that point over there are going to balance, right? And that happens for every single point. So the fulcrum's going to be in the center. But what happens now is you're like, oh, well, this point over here on this far extreme edge, it probably is not going to balance with this point over here. Because first of all, they don't form they don't on a line, right? So you get these like weird shapes. So it's like, where the hell would you balance this? So that's what we're gonna talk about. Cool, cool, cool. It's like, so how would you do this? Okay. So we have some names for these things. These like thin discs that we're balancing. They're usually called lamina. And there's two different centers that we're going to talk about. There's the geometric center. That's called the centroid. Now, that will be the same thing as the center of mass if the density is constant. So like if your lamina has constant density, then the center of that object, which we call the centroid, will be the center of mass. But if like some parts are more dense than others, the center of mass may not necessarily be the centroid or geometric center of the object. so I'm gonna insert a axis thing here. So let's say you have your axis, and let's say that you have this function f of x, and you're interested in your lamina is going to be under f of x between x equals a and x equals b. So does it make sense that your object's going to be between x equals a and x equals b, above the x-axis and below y equals f of x? Right? Sort of like, remember how we would find the areas of these things before? Okay. So we want to find the geometric center of this thing. So you can think like there's a bunch of points on here, and at every single point you have some mass, right? Okay, and you want to find well, where do I place it so that this thing balances? Okay. So that's the goal here. Okay, but you have an infinite number of points, and that's sort of an issue for us. So what we're going to do is, remember how we always partition and approximate? So we're going to start off by breaking this up into 4 pieces, like what we always do. And we get our 4 rectangles. There's one rectangle. There's another rectangle. There's another rectangle. And then there's another rectangle. So you've got x0, x1, x2, x3, and x4. So these planks look more like the one-dimensional case. Does that make sense? So if you break this mass up into planks, each of these planks has a center. Okay. So each plank has a center. And what do we always call those midpoints? Let's look at one of them. So where those little centers are, what have we been calling that center point right there? I always use a symbol for it. Between x1, x2, x star, right? Okay, so each of these things has an x star. So what you can do is imagine that all of the mass has been placed on that line at x star. And then what you can do is you can find out, well, where you would need to balance it. Okay, so where's the balance point going to be if the density is constant? There we go. So where will that balance point be? Right here, but how would you describe that point? Yes. Okay, so that balance point right there will be f of x star divided by 2. Okay, so in other words, if you look at each of these planks, it has a moment. Remember, the moment is the mass times the xi. So how much mass does this plank have? So the mass of a plank is its density times its area. And what is the area of this plank? It's delta x wide, and how tall is it? F of x star. Okay, so the mass of the plank is your density times f of x star times delta x. Alright, so that's your mass formula for each of those planks. Now we want to know for each of those planks, what's the value where the moment is. And that is just like what we said, f of x star over 2. So you're going to just add up that moment formula, which you can rewrite as, so I'll just write this as my moment for x is the sum of I equals 1 to n of rho. Now what's going to happen to my f of x star? There's 2 of them, so it's going to be rho f of x squared. It's going to be over 2 times delta x. Now, this is a approximation. An approximation with imagining that I have just 4 of those little strips. So how would you get the actual answer? Like, what do we always do? What do we always do to this Riemann sum to get the actual answer? You would integrate, which means that this would turn into this integral, which would be the integral from a to b, and then you pull everything out. You're going to get rho over 2 f of x quantity squared dx. Boom. So that's what your x-coordinate for your centroid is. Okay, and it's going to be a similar thing to find the y-coordinate. So if you want to find the y-coordinate, the only difference... Oh man, let me think of how I should say this. Oh man, I think I'm too hungry, and I'm like trying to think, but I'm like turning up a blank. I think we're just gonna end early today, and I'm gonna finish this tomorrow. Just I feel the drop in blood sugar. Why do we square it? Because there's an f of x from this one, and there's an f of x from that one. So I think we're just gonna end early because I'm feeling super hungry. Yeah, I'm gonna be releasing it. It's gonna be a take home. So we're just going to have class, and then I'm going to release the midterm at the end of it. No, I just got rid of that. I figured I wouldn't torture everyone. Yeah, what's up? Oh, let's see. What section are we on right now? We're on 2.6. So we'll cover up to 2.5. Okay. Awesome. Yep, you were here. Okay, let me click stop record. Yeah, we'll lecture tomorrow, and then I'll also give you the, what's it called?